Swayam Prabha. Digital India. Educated India.
Hi, welcome back. So last time we started speaking about the Cape-Salin model, right? And so essentially, these are things which you, I think you're familiar with. You run ANSYS, and then you, what's a turbulence model that you will use, and this is very typical, and you talk about that, right? That I use a Cape-Salin model, K-omega model, and so on and so forth, right? So I'm just trying to sort of briefly describe what exactly are we talking about here, right? So, like we started last time, right? So the Cape-Salin model essentially consists of solving two equations, right? So here we have the turbulent K equation, right? And we described this last time. And okay, so we spoke about this one equation. We kind of stopped here, right? So we need to speak about the other equation, right? So because this is a model which consists of it consists of solving two equations, right? Okay, so mean flow and turbulent K equation is this, and we use a gradient diffusion hypothesis to model the flux, right, which is given here. Okay, so let me sort of start from there. Okay, turbulent Prandtl number, right, for the K right is essentially is taken as is considered as one, right? So let me write this again. So using a gradient, so the let me write this, okay? Now mean flow and turbulent equation, okay, and this was flux, production, epsilon, diffusion, right? So where this T plus, T prime, right, is the energy flux, right, and that is modeled, right? So this is modeled using gradient diffusion hypothesis, and this is something we described earlier, right? So we model that, and that comes out to be gradient of this, okay? And there's the turbulent viscosity, right? So this is something that so we've described earlier. So this thing is essentially turbulent. Well, it should be viscosity coefficient, okay, I think, right? And this is the turbulent Prandtl number. Okay, right. So essentially, well, if you sort of look at this, right? If you just look at this, what is this telling us? Energy flux. Energy flux. So energy flux is is proportional to this del k, right? So which means that there is a gradient of k, right? And energy flux is equal to that, is proportional to that. Yeah, the proportionality constant being a turbulent viscosity coefficient over turbulent Prandtl number, right? So if I were to sort of just say write this as an inference, okay. Okay, so essentially we're saying that physically, due to velocity and pressure fluctuations, there is a flux of energy down the gradient of k. So there is an energy flux, right, in a direction in which there is a gradient of the kinetic energy. I think you understand that. So there are fluctuations in pressures and velocities, due to which there is a change in kinetic energy. So the direction in which the energy flux is happening is along the gradient of the energy, right? So so let's just say that physically this means that due to velocity and pressure fluctuations, there is a flux of energy right, gradient of turbulent kinetic energy. It's like saying this is important because you need to know which way energy is flowing. So in the sense that if you keep a cup of hot tea, right, what will happen to it after some time? It will become colder, right? It'll yes, its temperature will decrease, right? Now, why wouldn't this? Why wouldn't it like become further hot? Why wouldn't this become further hot? Why wouldn't it become hotter instead of sort of cooling down? Why would it not become? So when I say about the direction, right, the direction of the flux, so there is a change in temperature, right, in the cup of tea, right. So why is the temperature change? The temperature change so therefore there is a exchange of heat, right, delta Q. Now why is it important that which way the delta Q? As long as I have a delta Q, there is going to be a change in temperature, right. But it is that second law of thermodynamics, right, which tells us that which direction this change is going to happen, right. So this here, so this flux here, so when I model it using this gradient diffusion hypothesis, right. So I'm using this hypothesis. So therefore this relationship is essentially telling us that the flux is happening in the direction of gradient of k, energy change. And this becomes important, right, because you have energy yes, you have energy entering into a turbulent flow at the largest scales, right, and then they are transferred to smaller eddies. And finally, when it's sort of beyond a certain length scale, it's diffused, right. So it's important that how this energy flux is happening in which direction. It's not the other way around. Energy is not being transferred from smaller eddies to bigger eddies. It's actually the other way around. So there is a direction, right. So the energy flux here, which I'm modeling again using gradient diffusion hypotheses, is being transferred, right, along the gradient of k, right. And of course, why is there an energy change or why is there an energy flux? Well, that's because there are changes in velocity and pressures, of course, Okay, so that, right. Now there are advantages of, obviously that's why we are modeling it, right. So mathematically, this gives us smooth curves, right? Smooth solutions, and a boundary condition can be imposed on K, right? So let me write that down. So physically, right, this means this. Okay, then let's just say mathematical simplification. Okay, and mathematical simplification is modeling the term this way, right, yields smooth solutions okay, and a boundary condition can be imposed on the boundary of the solution domain, can be imposed on K everywhere on the boundary of the solution domain. Okay, right? Then, so therefore, I mean, we can just write the equation in this fashion. So the first equation that we just said. So what I'm going to replace this term, replace this term, right? Using I'm going to model it, like this. So then I can write out the equation. Therefore, turbulent K equation is essentially, right, is equal to this, right, and this is essentially the model transport equation for K, right. So this is the model transport equation for K, right? Okay. I'll give you some values. I think it's best to sort of write down these values here itself, say something about these. Okay. Now, okay, epsilon okay, all right. Now, so that's about the model transport equation for K. Now, the model transport equation for epsilon is entirely empirical, right. So, this one is now the model transport equation for epsilon, right, is entirely empirical, okay, and that is okay. See, we again use the gradient diffusion hypotheses, right, to model the flux. Okay. These are constants. Okay. Then I'm going to call this as 2, right. This is the model transport equation for epsilon. Okay. Now, let me give you some standard values, right. These are from Launder and Sharma. So, these are some standard values, right. Okay. So, these are okay. Okay. Epsilon, sigma epsilon is this, right. And so, I wrote this C mu. So, that essentially comes the turbulent viscosity, right. So, the turbulent viscosity is now modeled as, okay, diffusion, right, where this C mu is 0.09, right. That is that. So, if I'm going to go to another page and then say that in a simple turbulent shear flow, the K model yields okay. So, essentially, so we are basically saying we have these two equations, right. Okay, let me, okay. So, we have essentially this equation, right. This is the model transport equation for K, and this is the model transport equation for epsilon, right. So, these are the two equations which are solved in a K epsilon model, right, turbulence model, and I am sort of giving you brief ideas about what exactly we are doing, right. So, as you can see, so there is a rate of change of the turbulent kinetic energy, rate of change of diffusion, right, and this is the so this here is the convective part, then you have a production, right, and then again you have a the convective part here, right. So, and in a simple sort of turbulent shear flow, this will essentially yield me components of velocity in this fashion, right. I will get components of velocity in this fashion. Okay. Now, one more case is that if I have homogeneous turbulence, right, if I have right, What does this mean? This means that the convective change, homogeneous turbulence, the turbulence is not changing in any direction. So, then the convective change becomes negligible. So, if you look at these two equations which I have highlighted, what would the equations become? You see what will the equations become? So, then the equations become right. Right. Okay. Right. Now, so notice I write, now I have changed the derivative. So, here I had this notation, here I had this notation, and now I am simply writing it in this fashion. Is that right? Well, since I said homogeneous turbulence, which means this convective change is 0, therefore, when I say total change, right. So, this total change in 0 is total change in the parameter is nothing but the change in time, change that is happening over time, right, because the convective change is anyway 0, right. Makes sense? Okay. Right. So, that is really about the K epsilon model, right. So, this is a 2 equation model, and this is the K epsilon model, right, and you know of another one which is the K omega model, right. Okay. Now, let us go and see what that what that is like. Okay. And the next thing is the K omega model. How do we use this? Okay. Okay. Now, in here, okay, there is a model equation for omega which looks like this. Okay. So, the model equation for omega is epsilon like this, right, and then we write it okay. Is that right? Okay. Now, we had a K epsilon model, right, and now we are writing the omega in terms of epsilon and the K kinetic energy, right, and then we just simply sort of replace the second equation in the K epsilon model, and we write it in this fashion, right. So, essentially what is the difference between the K epsilon model and the K omega model is that we are writing the omega, right, in terms of the epsilon. So, it is kind of derived from the K epsilon model itself. Okay. So, let us just say epsilon, right, and we get, what do we get? right. So then I get this. Okay. Okay, let's just go back, right? So we have C epsilon 1 here. Let's just go back here. Okay, so these are the values we were using for K epsilon, right? Okay. 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 Right. So that is essentially your, the K omega model. So here are also two equations. So one is the K equations, just like the K epsilon model, and then we have the equation for the omega, which is actually which follows from the K epsilon model as well, where we write out the omega in terms. We derive the omega from actually the epsilon in the K epsilon model, and then we develop the equation in such a way, and then the equation kind of looks like this, right? So equation looks like this. Okay, so so this is the second equation that we are going to solve in a K omega model, and this is the second equation which we, this is how the second equation looks like. This is the model transport equation for epsilon, and this is the model transport equation for K. That changes, this one changes, right? So let's just say this one is the second equation. Okay. All right, so that's that. There is one more method that I will. These are terms which you come across and which are simple. I mean, it would be nice to know what exactly this. When you say turbulence models, what kind of what model are you choosing, and you should be aware, right? You should be aware of what exactly are we doing, right? Okay. Now this one is the Splat-Aramarus equation. Splat This is interesting. This is a one equation model. Okay, this is a one equation model, and that equation is essentially solve one equation, right? Right. So this is a one equation model, right? And here this SV is a source term, right? And depends on laminar and turbulent viscosities. Okay. Now, mean vorticity, okay, or rate of rotation, right, turbulent viscosity gradient, right, and distance of the nearest wall. Okay. So, so I think that is it really. That's I mean, the turbulence models that I really wanted to talk about is the Spalart-Allemaras equation, the K epsilon, the K omega. Okay, and so to kind of sum up, okay, to kind of sum up all these things. So we sort of started out, okay, all right. So we basically what we started doing is that what we started doing is that we looked at the turbulence domains, right, and we saw that whether it's the viscosity, whether it is the length scales, right, and the Reynolds numbers, which are really spread out far. Right, the ranges are really very large, and there are zones inside of those which are not exactly, evenly distributed. There's not even a question of that. So it was becoming really very difficult and computationally very expensive to calculate, right, to resolve all these length scales and all different Reynolds numbers. So then we said, okay, is it possible to do something else? Is it possible to sort of not consider a few and yet not go too far away from how the laminar flow, the turbulent flow looks like? So we looked at all those things, right? So we did look at. I think we drew up a. Okay, let's just see. I'll try to pull this up. Yes, so this was so we got this domain, right? We got this domain typically, and so K max eta. This is we drew a domain. This is a spherical domain of radius K max, right? So in here. We have this highlighted zone here. So we basically said that all the modes which are present in this zone, right. So this zone is guided by, this is the maximum is K max, and it's starting from K di, right. So this is the mode where, so these are the length scales, right. So the dissipative modes lie in the shaded area. So the maximum number of which are dynamically significant, okay, rather the modes which are dynamically significant are all present in this zone here, okay, and this is the dissipative zone, and this small one is where the peak of the energy spectrum lies, and the inner the sub range, right, energy containing zone, which is in the dissipative region, is about 0.02%, I think, right, as we said last time. So, and that also lies within this blue shaded zone, right. This is something we said, and based on and then we also saw that the computational cost really increases steeply as Reynolds number of the turbulent flow cube of that, right, and Reynolds number of the microscale microscale movements of length scale, which I am representing by lambda. So, 6 times of that. So, it increases really very sharp, right. So, to capture that kind of Reynolds numbers, right, and to sort of move between so many length scales is definitely a challenge. And so, then what we said, what can we do, right, what is it that can we do? I think the first thing we said is, okay, can we disregard some of these motions, and it still sort of get a fair bit of idea of how the turbulent flow looks like. So, I think that's what we did, right. That was the starting point when we said, only these modes can be resolved, or only the energy containing modes can be resolved, and so on and so forth. So, we did that. Okay. So, that's where we came upon these things, right. Low wave number forcing, I am not going to go into the details of that, but just point out that about less than 0.02% of the modes represent the motions in the inertial subrange. Okay. So, now the energy containing modes are very small, but then are very small, right. However, and they are also sort of located, I mean they are located in a very small range, right, in a very small range of motions. So, it kind of is easier to sort of locate them and go ahead and resolve those, compared to the others which are really spread over a large range. Okay. So, I think the one thing that we did was a low wave number forcing, which is actually, which was interesting. We kind of do that, where we were definitely able to get up with forcing Reynolds numbers from 60 to 180. We were definitely able to do that, right. So, we did something very unnatural, which is providing energy to the low wave numbers, and hence these are unnatural and they do not follow Navier-Stokes equations. They do not give us everything that we need to know, or they are not telling us all truths about the turbulent domain, but they do give us some information, and we sort of can live with that. Okay. Okay. So, in LES, right, in LES the energy contained modes, only the energy contained modes are resolved. Effects of unresolved modes are basically modeled, right. So, this is where we come upon this, these are modeled. So, these are actually calculated, the energy containing modes, and whatever we can't, so effects of the unresolved modes are modeled. Okay. Then we use a term of constant, a term called hyperviscosity, right, nu h, right. So, which also sort of, if I use that in a way in wave number space, is basically makes the dissipative region smaller. So, the region is smaller, so I have less number of modes to resolve, right. And then of course, we have sparse mode methods, right, where the energy containing modes are completely resolved, right, and for the higher wave numbers, right. So, higher completely resolved. For higher wave numbers, only a fraction of the Fourier modes are represented. Okay. Now, so this is something that so this is where the modeling thing comes in, that even if I sort of look at the domain and say, okay, I am going to resolve only these modes, typically what we can see is the energy containing modes. I can do something to sort of reduce the size of the dissipation zone, right, which is also which is what I do, hyperviscosity. I still need so basically all I am saying is I am going to kind of choose to calculate, choose to calculate only these, motions, right, because I am restricted. And if in that case, then the modes that I am not able to resolve, what do I do with them, right? So that's where the modeling comes in. So that's why we said, okay, so that is also necessary. So so then we came up with, that's where the turbulence modeling thing came up, and we started with the K epsilon model, right. So K epsilon model, right. So this is the K epsilon model, where essentially I have two equations, one for K and the other is for epsilon. Okay. So this is the two equations, 1 and 2 here highlighted for K, the model transport equation for K and the model transport equation for epsilon. So these are the two equations that we have, right, which we solve. And here the flux bit is usually is modeled with the gradient diffusion hypothesis, which is again something that we learned in a previous class. And if I solve these equations, then this is a solution I will get, right, and it should give us information about the turbulent flow domain. The equations become quite simple if I use a homogeneous turbulence, which means that the convective part of the flux goes to 0, and we have something like this, the two easy equations. Okay. Then we have the K omega model, where this is also using two equations. The first one is the model transport equation for K, right, which we use, and the second one is where we use something for omega, and this omega, however, is again derived from the K epsilon model, right, and it looks something like this, right, here. And then I write out the equation in for omega in this fashion. I have a convective term there, and for simplicity we assume this, then we get this, and this is the entire equation that we get, and you can see this is the convective term, which is interesting, right. This is the convective term. So this is the convective term where there is a gradient of the diffusion, and this is interesting. There is a gradient of the diffusion in the direction of the gradient of the kinetic energy. Okay, that's the K omega model. So both of these essentially have two equations, right? Two equations each to solve, and they use the gradient diffusion hypotheses to model the flux, right. If you see all the fluxes are essentially modeled on that hypothesis. Okay. All right. So then finally, we also use a Spellat-Alamaras equation, and this is it's a one equation model. It's a one equation model, and we see that so essentially we have a convective term as well as a source term, and we essentially, this is an equation to figure out the rate of change of the kinetic, the turbulent viscosity coefficient, right. We write it like this, and the source term, so the source term here, it's SV really, so that depends on the nu and nu t, right, and mean vorticity or rate of rotation, turbulent viscosity gradient. Okay, this is for the nearest wall LW. Okay. So I think that's all as of now. That is all to talk about. I think where we are going next to look at some CFD, right, and see how those equations, etc. We'll sort of write these equations down and see what these mean, right, and sort of get a feel for doing this ourselves. Some of you will, when you do research, are probably going to code these in, and you're going to write out these equations, and when you do that, that's good. But a lot of you we'll probably not go down that, probably not even write codes, but it will be interesting to sort of see that, okay, now I have all these complicated equations. Okay, so say I go to a domain, right? I go to a domain, right, and I look at this term. For example, I look at this term, the second term on the right hand side, right, of this equation, right. So what does this mean in terms of, I have a domain and I have a production, I have an omega and I have a k, right. So what do these mean? I have this domain here, and so what is the production, what is the omega and what is the k there, right. So I think, so how do we do that? Right. So typically in CFD what we do is, so this is an equation which will need to be solved, and obviously this is not, I don't have any analytical solution for this, right. So how do I solve this? How do I go about it, right? So that's where the CFD, computational fluid dynamics, comes in, and I think we will sort of look at equations specifically, and it will be a fun thing to do, and we'll see whether these things make sense to us. And all these notations, etc. Do they sort of make sense to us at all? Okay. In that context, so that I don't have to sort of repeat this next class, I'll just write out just to remind you some basic CFD formulae, right, which we will use. Okay, I'm not going to repeat that next class, since I'm sort of putting together everything. Okay, so for example, so if I have a grid, essentially, right, so if I have a grid something like this, usually these are equally spaced. Okay. Right. So I can have right, let's just say that. Okay. And shall we draw an axis system? I think we should, right. Let's just say so this line should be aligned to the x-axis. Please forgive my artwork. So that, okay, so that this is a delta x, this is a delta y. Okay, so then this is called central difference formula. Okay. So, okay. Okay. So, this is f dash, so prime of the function, which is the function of x I. So, I can say it is, I am just writing it out, okay, is basically equal to okay. So, this, so y I plus, so I is here, right, y of I plus 1. So, this is I plus 1, right, this is your I plus 1, and this is your I minus 1. So, when I say this, I mean this location, okay, and okay, is equal to y I plus 1 minus 2 yi minus yi minus 1 by h square. Okay. Then we have a backward difference okay. Okay, so essentially I am calling this as H, delta 1 delta H, okay, that, and forward difference formula, okay, so which is